Hello, grade 10s. We're going to finish the states of matter and the kinetic molecular theory in this lesson. In the last lesson, we ended off by discussing the heating curve and the cooling curve of substances, and we're going to start this lesson by looking at the kind of question on the heating curve or cooling curve that you could expect to get on exams. So the heating curve for a pure substance at standard temperature and pressure is shown in the graph below. So we're going to consider this graph and we're going to answer questions on it. So the first question is, what is the boiling point of the substance? Now, you can look at this graph and analyze it. And we know that over here we have a solid, over here we have a liquid, and over here we have a gas. At this point of the graph over here, we actually have the process of melting, which means that the substance exists as a liquid and a solid at the same time. And at this point of the graph over here, we have boiling, where the substance exists as a liquid and a gas at the same time. So the first question is asking us, what is the boiling point of the substance? And we can read the boiling point of the substance at point X over here. Very, very importantly, we need to be able to figure out graphs and to understand the scale over here. Now, we've got 0 to 30, 30 to 60, 60 to 90, and 90 to 120. So that means that each of these blocks is going up in 30s. Now, if we count the number of little blocks over here, we've got 10 of them. 30 divided by 10 is 3. So that means that each little block represents 3. So if this point here is 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. So just double check. So we now know that each little block is worth 3 units. And the X point over here is one little block above the 90. So that means that the boiling point of the substance is exactly 93 degrees Celsius. You must include units of measurement. The next question asks us about the melting point. So we need to read off this point on the graph. So we've got 60 minus 3 minus another 3 to reach this point. Or we can go from 30 and then go 33, 36, 39, go up in 3s until we reach this point over here. So the melting point of the substance is exactly 54 degrees Celsius. Again, remember your unit of measurement. Is the substance water? Provide a reason for your answer. We know that the melting point of water is 0 degrees Celsius and the boiling point of water is 100 degrees Celsius. And that is not the case for this substance. So the answer is no. You can either say that it doesn't have a melting point of 0 degrees Celsius or that it doesn't have a boiling point of 100 degrees Celsius to answer this question. What is the physical state of the substance at room temperature? Well, we know that room temperature sits at 20-something degrees Celsius. And anything below 54 degrees Celsius, at those temperatures, the substance exists as a solid. So at room temperature, the substance will also exist as a solid. And what is the physical state of the substance at point X? Now remember that during a phase change, the substance actually exists in 2 phases or 2 states. And during boiling, it will exist as both a liquid and a gas. At a macroscopic level, and remember a macroscopic level means at a level of things that we can see and we can measure. So what happens to the temperature over here while the substance is melting? Well, simply reading off the graph during melting, the temperature doesn't change or the temperature remains the same. Now, explain it microscopically. That means that you need to explain it at a particle level. And when you get this kind of question, there's a way that you have to answer it. There's a model answer. So I'm going to take you through it. The first statement that we're going to make is that the temperature remains the same, as we already said in the previous answer. And that means that the kinetic energy of the particles remains the same. So this is key over here. Secondly, we need to state that the energy is going into weakening. This is the key word here, weakening the intermolecular forces of attraction. You have to say it in full, between the particles. There are no shortcuts here. And finally, we need to state that because the particles move further apart, their potential energy increases. So this kind of question would be out of 3 or 4 marks, and this is the model answer. This brings us to Brownian motion and diffusion. Now, Brownian motion and diffusion are two things that were observed macroscopically that made scientists believe or understand that matter actually exists of teeny tiny particles that we cannot see. Now, Robert Brown was a botanist, and in the 1800s, he observed pollen under a microscope. And what he found was that the pollen erratically jumped around. So there was no breeze or anything like that to impact the movement of the pollen particles. And you would expect pollen particles or any particles due to gravity to just land on the surface. But again, instead of landing on the surface, he found that pollen or dust particles would just erratically jump around. He didn't know what was causing this, and we didn't know about atoms at the time, so he theorized that the pollen was alive. But later scientists understood that actually the pollen was randomly colliding with the particles that make up air. Now, we can't see the particles that make up air, but they're there, and they're impacting the pollen particles. The small air particles can't be observed under a microscope, but the pollen particles can be observed under a microscope. So what we're actually seeing under a microscope is a pollen grain. We are not seeing the air particles that are much, much smaller than the pollen grains, but there are many, many of them. They are constantly bumping against the pollen grains and causing the pollen grains to move around randomly. Brownian motion is the random movement of microscopic matter like dust and pollen that is suspended in a fluid like a liquid or a gas. Liquids and gases are considered fluids because they both have freedom of movement. Solids are not considered fluids because they don't have freedom of movement. If you have dust or pollen suspended in a liquid or a gas, you would observe Brownian motion. This random movement is caused by the microscopic particles in the surrounding medium that are colliding with the microscopic matter. So the medium that we're talking about would be the liquid or the gas. So the liquid or the gas particles that make up the medium would move about the microscopic matter like the dust and the pollen. So this was the first evidence that matter exists as discrete and separate particles that are very, very small, which we now know to be atoms, or atoms that are bonded to each other that are still very small, called molecules. Now, I'd like you to watch these videos on Brownian motion because one gives a really good explanation and the other one shows you dust under a microscope, so you can actually see this random movement under a microscope in this video. And what is diffusion? Well, this is a definition that we need to be aware of. Diffusion is the random movements of particles of fluids, meaning liquids or gases, from an area of higher concentration to an area of lower concentration until they're evenly distributed. So the process of diffusion will end when the particles are all evenly distributed throughout the medium. The particles of fluids, meaning the particles of liquids and gases, are constantly moving because they have kinetic energy. Obviously, in liquid form, they slip and slide, and in gas form, they have more freedom of movement. But regardless, this is the reason that fluids mix without any outside influence. So even without any outside influence, all the particles will get distributed evenly through a medium, and this is a process called diffusion. So for example, smoke from a chimney will diffuse into the air. This means where the smoke is being released, it is at high concentration, and the smoke is at low concentration in the surrounding air. So the smoke will move from an area of high concentration into the air, which is an area of low concentration of smoke, until evenly distributed. So essentially what that means is that pollution gets evenly distributed in the surrounding air with time. If we pour a few drops of food coloring into a glass of water, then we will see diffusion of the food coloring into the surrounding medium, which is the water. Now, the diffusion process will move the particles from an area of high concentration over here to an area of low or even no concentration until evenly distributed. And once evenly distributed, the diffusion process would have ended. How are we able to speed up the diffusion process? Well, anything that adds kinetic energy to the particles will speed up the diffusion process. So if we stir the mixture, we're adding mechanical energy to the particles. If we heat up the mixture, we're adding thermal energy to the particles. And either way, these translate as kinetic energy, allowing the particles faster movement. However, diffusion will take place even without any outside influence. And diffusion is further evidence that matter exists as discrete and separate particles that are very small. So Brownian motion and diffusion were both early proof of this statement over here. And this is a really nice video that looks at diffusion through air, through vacuum. It looks at rates of diffusion of different substances. So I really recommend that you watch this video. And that brings us to the end of kinetic molecular theory. The kinetic molecular theory is a model that explains our macroscopic observations, the things that we can see and measure at a microscopic level, a particle level that we cannot see. Kinetic molecular theory compares the movement of atoms and molecules in their different states, so in a solid, a liquid, and gas. It also explains our macroscopic observations by describing what happens at a microscopic level. So it explains the heating curve, the cooling curve, Brownian motion, diffusion, and that allows us to understand the behavior of atoms and molecules.